All right, we're on to number 11 for the 2013 Algebra 2 exam in the Pacific High School Math Competition. Number 11 is as follows. A crew rows 4 miles downstream and back the same distance in 1 hour. If the stream flows at 3 miles per hour, the crew's rate of rowing in still water would be, in miles per hour, one of these 5 options. Okay. Full disclosure, I had a really tough time with these problems when I was taking algebra. So, if you had a tough time with this too, we're in the same boat. Or we would have been in the same boat. Now I know how to solve these problems pretty well. Okay. So this, let's look at some of the key terms in this problem. There's, 4 miles downstream and back. Same distance, 1 hour, miles per hour. This screams a distance, rate, and time problem. And the relationship between distance and rate and time is distance is equal to the rate times the time. I'll give you a very quick example. If you're going 60 miles per hour, which is your rate, for 1 hour, which is your time, and you want to find out how much distance you covered in that time span, that's 60 miles per hour times 1 hour. What do you know? These units cancel, hour. Then you're left with 60 miles, which is your distance. This unit canceling is referred to as dimensional analysis. You might have seen this in your chemistry class if you've taken chemistry. Okay. So let's get back to it. Just give me one moment. I'm running into some technical difficulties. Okay, great. So let's scroll down a bit. Give ourselves some more room. Okay, so we know that the crew rows 4 miles downstream, and then they row that same distance back in 1 hour. And we're given the rate at which the stream flows per hour. And we're asked to find what the rate of rowing of the crew is in still water. Okay, so I'm going to break this down into 2 components. Downstream, the downstream journey, and the upstream journey. Maybe I should do them in different colors. Hopefully it doesn't, hopefully it's just as clear if I use the same color. Anyway, so when you're going downstream, you're going with the stream. So let's give a variable to the unknown, the crew's rate of rowing in still water. Let's call that x. And we know the downstream rate is 3 miles per hour. So when you're moving downstream, you're moving quicker because the stream is helping you push along. However, your crew is also rowing at that speed. So when you're downstream, you add the 2. So that is the rate. So I'm going to call this rate of downstream, or R sub D. This is just notation to help us remember what this quantity represents. When you're going upstream, though, you're fighting against the stream. You're moving up, but the stream is pushing you back. So you have your rate of rowing in still water minus the stream rate. Okay, so you're going at x minus 3 miles per hour, and that is your rate upstream. Okay, awesome. And in both cases, let's use a new color for a new quantity, I guess. You're going 4 miles. You go 4 miles upstream. You're going 4 miles downstream. Scroll down. So we have a rate, we have a distance, and we also know that both of these things happen in 1 hour. So, you know what this is what I'm going to do. I'm going to switch colors, first and foremost. The time of the journey, or let's just say the total time, which is t, is, and we can, d equals rt. This translates to time is equal to distance divided by rate. So the time is 1 hour. But that's also the distance that was traveled upstream divided by the rate upstream, mph, plus the distance that was traveled downstream divided by the, plus the rate that we were going upstream. So we know that the total time of the journey is 1 hour, and the total time is just the time taken to go upstream plus the time taken to go downstream. Okay, now that we have all of that, this is starting to look like an algebra problem. So let me, I think it's helpful to keep the units. So we'll have, we're trying to find x. Okay, we're gonna do some classic algebra. What we're gonna do is we're gonna get these nasty fractions out of the way by multiplying by the denominators. So we're going to multiply on the left-hand side 1 hour with x minus 3 miles per hour. And then we're going to multiply that also with x plus 3 miles per hour. This is the left-hand side. And what we do on the left-hand side, we have to do it on the right-hand side. And we're going to... Okay, so on the left-hand side, we've clearly multiplied by x minus 3 miles per hour and x plus 3 miles per hour. And on the right-hand side, what this looks like is if I multiply this term over here by x minus 3 miles per hour, we get rid of that denominator because of a giant 1 canceling. But we also multiply this by x plus 3 miles per hour. So now we have 4 miles times x plus 3 miles per hour plus, and the same logic for the other expression, 4 miles times x minus 3 miles per hour. Okay, great. Awesome, awesome, awesome. Now, when you're multiplying time by rate, you get distance. Okay, we're going to use a new color just to keep things visually interesting. And to make sure that it's a visual indicator that we're moving on to the next step. What this is now is we have time and we have a rate. So we have x squared minus 9. And this is, what unit is this? is this in? This is miles per hour squared times hour, which is x squared minus 9 miles squared per hour. It's weird to think of miles per hour squared and miles squared. If you want to, you can safely ignore the units because all we're solving for, all this algebra is leading to solving for x. And x, as we notated earlier, is the rate at which the crew rows in still water. So you can ignore the units. It's weird to think about miles per hour squared. What does that mean conceptually or in the real world? What does miles squared per hour mean in the real world? And I share that same confusion with you. I don't. It's a strange thing to think about the unit this way. But I'm just keeping the units there because as a sort of a sanity check. Because at the end, when we solve for x, it needs to be in miles per hour. So it's a way to make sure that I know I haven't made a mistake in my algebra. Okay. Finally, we're on to the right-hand side of the equation. This is 4 miles times x plus 3 miles per hour. This is 4x plus 12. This is, again, miles squared per hour. Horrible handwriting, I know. And we see something similar with the other expression, 4x minus 12 miles squared per hour. Okay, great. Awesome. So we have x squared minus 9, and this is the, let me notate that this is the left-hand side of that equation. This is the right-hand side of that equation. And they're still equal to each other. So right now, we notice that both sides have the same units. We have miles squared per hour for every single term here. So I'm going to safely now ignore the units because it's just getting way too hairy to write it, and it's taking too much time to write it all down. So we have x squared minus 9 is equal to, I'm going to sum these, 8x. Okay, this looks very familiar. This looks like a quadratic because it is a quadratic, and we're solving the quadratic for its roots. We'll do that by factoring. I knew to go from this step to these two factors because I asked myself, what two numbers, when multiplied together, give a negative 9, and when added together, give negative 8? It's negative 9 and positive 1. Finally, we have our solution, which is x is equal to 9 and negative 1. And those are our two solutions. This is the rate at which the crew travels in still water, 9 miles per hour or negative 1 miles per hour. I'm not so sure if negative 1 miles per hour means anything. I mean, I guess if you're going backwards, but let's not get into that. Let's stick to the positive number, 9 miles per hour. Let's look at our answer choices. And what do you know? One of the answer choices is 9 miles per hour, and that is our answer. Let me make sure that's correct. Yeah. Okay, let me doubly make sure because I don't want to make a fool out of myself on YouTube. It is 9. Okay, great. We're done. If any of that was confusing, just leave a comment. Yeah, I hope that was clear.